All right, explain 3. We're going to go on to solving a real-world problem using a fitted exponential function. So here they say that the Texas population increased from 20.85 million to about 25.15 million from the year 2000 to 2010. So, assuming an exponential growth, because it did grow, right? We're going to write a model where x equals 0. So for 2000, is really 0, and 2010 is really 1. And their partners were 20.85 million to 25.15 million. First thing we're going to do for this model, we'll see that it did start at about 20.85 million people. So we're going to plug that in for our A value because that's where it started. For our B value, we're going to write in about 1, since it is 1, and 25.5. We're going to plug that in for f of x and for x as well. So that would be 1 and 25.5. What we're going to do is we're going to solve for b. So what is the opposite of multiplying? Dividing, right? So we'll divide both sides by that much. And we're going to go ahead and figure out what 25.5 divided by 20.85 would be. Since it's b to the first power, we don't have to root anything or raise anything to a reciprocal power. Once we figure that out, we can figure out what our b value is. So that would be about 1.206. All right, cool. So that wasn't too bad. We can now know that our function's going to be about 20.85 as our initial a value and our b value of 1.206 to the x power, which means that our growth rate was about that as a decimal, which we can change to a percent by multiplying by 100. So go ahead and try that out. And if you did that, that would be about 20.6%. All right, let's move on to part B. So they're saying let's find the b value. If instead we use the power of a power property for exponents to rewrite the model so that b is a yearly growth factor instead of a decade factor. So let's say because there are, how many years are in a decade anyways? 10, right? So we're going to do 10 years in a decade. The 10th power of the new b must give the b value we got in the last one, which was about 1.206 for the whole decade. So what we're going to do is we're going to go ahead and solve b to the 10th power equals 1.206. Now the reason why we're putting to the 10th power, because remember there's 10 years in a decade. Let's go ahead and figure that out. So what would this be? So let's go ahead and solve for b. So here if I have to the 10th power, what is the reciprocal of 10 over 1? 1 over 10. So let's go ahead and work that out to figure out what our new b value is using our either graphing calculator or Desmos. Go ahead and work that out. And that would be about 1.0189, or if I make that equivalent to about 1.019. Okay, so if x is measured in years after the year 2000, the model would be the same a value, which was about 20.85, but our new growth model would be 1.019, meaning our yearly rate is, if we changed this part to a percent, we can multiply that by 100. Go ahead and work that out. And that would be about 1.9% growth rate. So that means our model could be given as 20.85, 1.019, and let's say if I still wanted to know an estimate of the 2010 population, I mean, I know because they give it to me in the problem, it's about 25.15 million, because that's what was in 2010. But let's see if 10 years later if that would actually still be the same. So go ahead and calculate that out. And you should have gotten something like 25.17. So the estimated model using this new ratio, or this new growth factor, is actually pretty close to what's actually there. Because in the problem they told us that the population is about 25 and some change, and this one's pretty close, 25 and some change. It's not that too far off. So this might actually be a better model to show growth rate of the population of Texas than the one we got previously, which was showing like a 20% growth rate. Alright, with that being said, let's go ahead and go to part C. So they're saying, okay, now that we have our growth model, go ahead and make some estimates. So they say the Texas population in 2013 is 26.45 million. How does this compare to the prediction made by the model? So let's go ahead and use our model to make a prediction and see how close it actually is. And that would be about 13 years. 2013 is about 13 years after that. We're going to use the model that we found in part B. Okay, so here let's go ahead and figure out what 20.85 times 1.019 to the 13th power, how much that would yield. So take some time to go ahead and work that out. And we would find that it would be about 26.63 million people here. So our prediction is a little off. In fact, it's about off. Let's go ahead and figure out how off it is. So it's a little off, but go ahead and figure out how much that that would be. So our prediction's actually off by about 0.18, and actually it's about 0.18 million people over, actually. So, and it's pretty close though. So we can definitely use this model to make some predictions. Alright, in part D, they're now asking us to make another prediction using the similar model for what the population would be after, or in 2035, which is about 35 years after. So that would be about 20.85 times 1.019 to the x power. Instead we'll put to the 35th power. And we're going to figure out about how many millions of people will be in Texas in 2035 using our model. So go ahead and calculate that out right now. So that would be about 40.3 million if you worked that out. That would be about 40.3 million people in 2035. Alright, for part B, we're going to go ahead and look at our data here. And it says the average revenue per theater for part B of the previous examples is shown in the graph. Well, that's kind of nice. Where week 0 corresponds to week 2 of the graphs from the previous examples. Okay, and they give us a regression model, which is nice. Okay. From week 3 to week 4, there is a jump of over 60% in average weekly revenue per theater. But the total revenue for the movie for a corresponding weekly fell about 30%. What must have occurred for this to be true? That the growth actually went up, as you can see here, right? So it did kind of go up. And then you can see that it actually goes right back down. So they had a sharp increase, and then it kind of drops back down in the viewership. So, well, I don't know about you, but when there's opening weekend, there's usually a lot of theaters showing that particular movie. A lot of theaters showing that movie. But as the popularity kind of goes down, you see that there's fewer theaters showing that movie. So that could explain why from one week it shoots up because there's a bunch of movie theaters showing that movie, and then it kind of dips back down, probably because there's just fewer theaters showing it, right? For part B, it says, let's say there's a new theater complex managed showing a similar summer movie in single theaters, and he worries about quickly dropping revenue the first few weeks and wants to stop showing the movie. Okay, so, and that happens a lot when we were watching movies. People just don't want to watch them after a while. Suppose you were advising the manager. Knowing the model shown reflects the long-term trend for such movies, what advice would you give? So if you notice that the viewership and revenue does go down, this is more your opinion, but go ahead and say, what advice would you give to that manager who wants to just altogether stop showing a particular movie? And go ahead and write a statement about that. So there's no really math involved in part B other than kind of just analyzing the data and making decisions with it. After this, they do want you to do number E into the packet, so please go ahead and do the Explain 3 number 9, and we'll see you on the next video.